I must confess, when I make these videos, it's unusual not to have a class in front of me. Yeah, like, where is everybody? But, alright, I just have to make an assumption everyone will eventually listen in. Okay, so we're going to define projections and vector components. Okay, that's something that's useful, and you'll see it in physics. If u and v are two non-zero vectors, then the amount of force from u in the direction of v can be represented as the projection of u onto v, or the component of u in the direction of v. This picture down here is going to explain it to you in r squared. The picture is the same in r cubed, inside of the plane that those two vectors are spanning, so I only am going to make a two-dimensional picture of this. But the notation is the projection of vector u onto vector v, and it's a scalar multiple of vector v. And here's a picture of it. Okay, we have, let's say, some forces acting in this direction, and we'd like to know how much of that force is in this direction. Maybe you're pushing something in the force in this direction, but that something is fixed to a track that's moving this way. And you're saying, well, that would be a kind of a dumb thing to do now, wouldn't it? Because if I wanted to get something to move on a track, I'd push it in the exact same direction, but not all forces work like that. For example, this could be an airplane flying this way, and this could be the wind, for example. So how much of the wind is in the direction of the plane, for example? That's what we're trying to see in this example. And so if this is vector u, vector v is this vector here, and we're talking about this vector v is just giving a direction, then this vector, the projection of u onto v, is a vector, and it's a vector that points in the same direction of v. As a matter of fact, it's a scalar multiple of v, showing this is a perpendicular projection. See the right angle here? It's showing how much of u is in the direction of v. Matter of fact, this plus this vector right here would add together to give us the vector u. So the dotted line is the component of u that's orthogonal to v. So vector u is this much in v direction and this much orthogonal to v. So u can be thought of as the sum of two forces, one in the direction of v and one orthogonal to v. So that's what a vector u is. And it wouldn't matter even if the vector u was back here, because then the projection onto v would be a negative number, and the orthogonal part, well, that would be a positive number. But you know, that force ultimately would be doing negative work in the direction of v. So can we find this projection using the dot product? And the answer is, well, of course. I wouldn't have given you dot product if you didn't need it for this. If you studied pre-calculus with me and studied vectors there, we would have found in that class COMP of u in the direction of v, the component of u in the direction of v, which is just the length of this line here, which you can use trigonometry to find. See, that's why it was appropriate for pre-calculus too. Also useful though in physics, just finding out what the length of this is. We will be looking at what is the vector here, which is just really this number times a vector in the direction of the unit vector in the direction of v. So, finding projections using the dot product. Here we go. This is what we're after here. We're going to find this projection right here using the dot product. Okay, so let u and v be non-zero vectors like these two. Then the projection of u onto v is given by a projection of u onto v. That's the left side of this equation. U dot v, see, there's a good old dot product, divided by the length of v squared. Now, in pre-calculus 2, that was all we wanted, but then actually over this wasn't even squared. It was just to the first power. because what we're doing, we're going to take u dot v over the length of v, which is what we call the component of u in the direction of v, but then we're going to multiply that by the unit vector v divided by the length of v squared, and that's why we have the length of v, v divided by the length of v, but because of this length of v in the component plus the length of v in the unit vector here, then that's going to be the length of v will be squared in the denominator. So if you take this apart, you can see that's what it is. This is what we called component of u in the direction of v, and this is a unit vector in the length of v. Let's just do an example. Given vectors u 4j plus k and v 2j plus 3k, find the projection of u onto v and the vector component of u orthogonal to v. That's going to make things interesting. So first of all, this projection is going to be u dot v. Okay, let's do that. 0 times 0 plus 4 times 2, that's 8 plus 1 times 3. 8 plus 3 is 11, divided by the square root of, the length of v squared. Well, the length of v squared is square root of 13 squared, so we'll just call that 13, times the vector v. And so that would be times 2j plus 3k. So in other words, it's 22/13 j plus 33/13 k. Note, this is just a scalar multiple of vector v, because it's something like this. See, this is vector v, this is the scalar multiple of v we just found. How much of vector u is in the direction of v? Now, the other part of the problem says, and the vector component of u orthogonal to v. Now, how are we going to do that? Well, it's going to be vector u minus that. Think about it. Remember, that's how you subtract vectors. This one minus this one equals this one. And that's what we're trying to find, is this one. So this vector minus this vector. That's easy. So it's this vector u, recall u is 4j plus k, minus this vector 22/13 j plus 33/13 k. Looks like I'm going to have to do a little work with fractions here. I guess 52, that's 52/13, so 52/13 minus 22/13 would be 30/13 j, and 13/13 minus 33/13 is minus 20/13 k. So there is the vector component of u orthogonal to v. So in other words, for this particular force here, this much is in the direction of v, this much is orthogonal to v. And it's interesting that this, I don't need to do an example in 2 dimensions now, because this whole thing took place in the YZ plane. Interesting, huh? So, what would the dot product, do you think, of this vector and this vector be? Just think about it for 1 second. What should that dot product be? In other words, what should the dot product of this vector, this vector and this vector, what should the dot product of these 2 vectors be? The projection of u onto v and the component orthogonal to v. What should it be? Well, the answer should be, well, they're orthogonal, so they ought to be 0. So if you notice that, multiply this by this, you get, let me see, 3 times 22 is 660, positive 660/13, and this times this is negative 660/13. Isn't that convenient? So you do get 0, and yes, you knew it was going to be that.